Okay, I started recording and the screen is shared, so I think we can start. I uploaded the video of last Thursday only this morning. Sorry for the delay. And let me just go here. So last Thursday, we introduced the use of R, and I am sure that it was not really easy. So I just wanted to repeat here today to make a summary of what we learned about the use of this software on Thursday, and in particular, just I would like to summarize the steps that we did, we followed in order to upload the data, because I think this was the tricky step, okay? So in uploading data into softwares like R, like MATLAB, Python, which we will introduce as well, it's a step that in some cases may not be so easy. First of all, keep in mind that we are still working on the console. And by the way, don't forget to install RStudio on your computer. I gave you the instructions to do that last Thursday, and it's videotaped the instructions. So if you still have some doubt, you can refer to me. But I think it should be very, very fine. And with RStudio, it will be easier to upload the data. But I think it is important that we also learn how to do it from the console in general, because it is a general procedure that can be followed also with other softwares. So let me just try to summarize the steps. Let me change the camera so that the blackboard is okay. The blackboard is on the screen. So what we did, is to put our data in a text file. The text file conventionally has an extension txt. So this is name file .txt. The text file has a nice feature that can be read by several software. It's like a universal format. It's just numbers or text, without any formatting, without any amenities, without any attempt to make it, to embellish it, to make it nice. So it's very much different from an Excel file or a Word file. The Excel file or the Word file, they are formatted in order to be able to be read by the specific program only, so Excel, Word, and in order to present it in a user-friendly way. In the text file, it's like a universal format, which can be read, as I said, by several platforms, and it's very essential. So in the text file, you can read it typically in Windows with Blocknote, with the Notepad. Blocknote is another editor. And in general, you can edit the text file with any text editor. There are several of them, text editors, okay? So given that it's a universal format, the easiest way to transfer data from a platform to another is to pass through a text file. So if I want to pass data from Excel to MATLAB, the easiest way is to pass through a text file. Let's say the most straightforward way, okay? So what we need to do is, for instance, if we have the data into Excel, we have to place the data into a text file. And the easiest way is from Excel, you cut and paste. You open Notepad in Windows, and then you copy from Excel and paste into the Notepad. This is very easy. And then you save the file with the extension txt, okay? And any other text editor can be used. I say this not only because there are several text editors that are available. I say this because if you use a different platform like Mac, you don't have Notepad, but Mac has its own text editor. So you can do the same thing, copy from Excel and put the data into the text editor. The same from the web. If you download from the web, typically you can select a format, like I did on Thursday during our lecture. So you can save in CSV or in text. What I suggest to you is to save in text, okay? The text file may be divided into several columns. So you may have one column here and another column here and another column here, and then you have the lines, okay? It is easier if you put the data into just one column, but if you have a matrix, the matrix has to be, of course, put in the Excel file, in the text file with columns and rows. This is no problem. And then you can open the text file with, again, with Excel. 1 second, because I think that I have people in the waiting room, yes. So you can open it in Excel, in Word, whatever, or you can upload it into R. So in order to upload the text file into R, what we did is to give the instruction, okay, name variable is equal to scan. First of all, here I'm writing in capital letters, you know that it's case sensitive R. So scan has to be written in lowercase, the name of the variable you choose. If you want capital letters, you can use capital letters. Just remember that is sensitive. Okay. And then we use the scan, and then you have to give the name, the file name. With the path. Okay. Important thing, file name, the name that you gave here. Okay. Problem here is that we have to give the path. The path is the way to follow into the hard disk to find the file. And it's like the address of the file in your hard disk. And then the name of the file is its name, but the address is given by the path. Now, if you are not familiar with the term path, storing directory, or directories, where to place files, try to get familiar with these concepts, because you are going to get a degree with some scientific basis, whatever it is, engineering, physics. So you need to manage the PC quite well. This is why we do these exercises. And in particular, you have to manage quite well the basics. So how to find the path of a file, it's the basic. It's the basic, okay? So try to learn it. In general, the problem is that Windows, it doesn't tell you the path. The Windows tends to present to you everything in the hard disk as a shelf, you know, with some drawers where files are stored, and Windows doesn't tell you the address. Unfortunately, in Windows, from this point of view, it's not really educational. If you use Mac, I think you are more familiar. What is a path? What is the architecture of the PC and the hard disk? Windows tends to give a kind of education that keeps everything a bit secret, okay? In any case, when you save a text file, typically Windows asks you, or put it in the documents, or asks you the directory. And then you can see with the file manager where the file is. So if you right click on the name of the file in Windows, it tells you under properties the path. Okay, so you can put the path here. And so, I mean, if you are not familiar with these concepts, try to get familiar. It's very easy. If you go on the web, you find a lot of very simple tutorials. Or if you really get in trouble, you can refer to me, okay? And you can refer to me anyway, okay? But I think it is easier for you if you find an easy tutorial in order to get this information. So basically, you have to give the address and the file name. Into R, keep in mind that it may be necessary that you give a double slash try. If you get an error, so R tends to use double slash to mean a slash. If you the slash is on the other, it's oriented in the other way. Okay. And try. If you get a file not found, you can try with the double slash. I think I didn't tell you this on Thursday. And if you put in Windows the file under documents, you can omit the path and give only the file name, which is easier. But try to get familiar with the path and try to get familiar on the usage of the path with MATLAB, R, etc. Now, another thing that we discussed, which I want to remind you, is that if you have a matrix to upload, like we had, because on Thursday I uploaded, you may remember, data that I downloaded from the web. I downloaded in a text file, but it was in the form of a matrix. So under the instruction scan, R reads everything in the file sequentially, and at the end of the story, a vector is uploaded. A vector is uploaded, not a matrix. If you read a matrix, a vector is uploaded because it reads the first line, and then the second line, the third line, and puts everything into a single column, into a vector. Therefore, you have to transform back the vector into a matrix. And what we did this. We did name variable with a different name, but you can use also the same name. And in this case, you overwrite the previous one. It's, we said array in lowercase, be careful, array, and then name variable. And then comma, second argument, we have to give the dimension, dim equal c, and then there is the vector and the vector of number of row, number of columns. This is what we did. Here, the tricky question is always, if I want to get back the original matrix, of course, the multiplication, the number of rows and the number of columns should match the number of rows and columns in the original matrix. But the question is, should I put first rows or first columns? Just try. I mean, it is very easy to try. You try, like we did the other day. If you may remember, I tried, and then I realized that it was the opposite, and switch them. Okay, and how to check if everything is fine? You can simply check by writing name variable one, name variable one, and then you give an index between squares. You can give 1 comma. In this way, it shows you the vector that results from the first row. And if you invert them, first column. And then you check whether it's the same column as the original matrix. It's very easy. If you see that they are switched, and then you change the order here. If you don't want to visualize all the numbers in the first column, because maybe the first column is 1 million data long, you can put here a range of indexes, 1, 10, 110, okay? You see only the first 10. You see how you can manage numbers, elements of vectors, elements of matrices. So you may think, oh, this is too complicated. On the other hand, think of the benefit. The benefit for with R, for instance, with respect to Excel, is that you can handle like 2 million of data, or I handled also 100 million of data with no problem. It's very fast. If you have to manage a huge amount of data with Excel, it becomes very slow. So this is a first criteria that you may follow. When you have to decide, I have to print a graph, I have to manage data. Should I use Excel? Should I use MATLAB? Should I use R? This is one of the first criteria. You try with Excel. If it becomes too slow, and you will see that indeed, if you reach an amount of data that is like 100,000, which is by far less than 100 millions, you will see that Excel becomes unmanageable. And any time that he has to recalculate formulas, 100,000 formulas, it takes like 30 seconds. It's unacceptable. It is unacceptable when you have to perform like 100 tasks in one day. You understand? If you take 1 minute more for each of them, at the end of the day, you work 1 hour and 40 minutes more, which is unacceptable. So if you have to manage a lot of data, you see that Excel becomes too slow. Then if you are able to use MATLAB, this is perfect. And if you don't have MATLAB because the license is too costly, then you use R, which is free. These are the criteria that allow you to navigate between platforms. But of course, in order to do that, you have to get the knowledge. And it's never too late, because once that you learn the first one, it's no problem. Okay, and one more thing. When we will have RStudio, it will become much easier to upload data, because there is a menu with data upload, and you can put the file name, and the path you can find it through navigation, so like in Windows, which makes it very easier, much easier. And so RStudio is simplifying things, but it's much better if you also know how to work with the console. And in RStudio, there is also a menu which allows you to import from Excel. I tried to use it, and I didn't find it very easy. You can try. And if you find it simple, just tell me, tell others. And I didn't want to spend much time, because I am so used to work with the console. I'm so quick with the console that I think the console at the end of the story is the easiest and quicker way. But if you want to try a direct import of data from Excel into RStudio, just try. It is and if you find good results, let me know. And if you succeed, I found that it's not easy, because you will see why. Because it's difficult to select the column, and the import, it tends to import all the data. And then in Excel, you may have a lot of data, and then to pick up the column that, or the row that I want to manage, to me, it resulted a bit difficult. But I don't have the amount of time that you have. Maybe that you find a good solution. So this is what we did. Do you have any question about this? Yeah, please. Okay. Okay. In any case, there is the video recording of this on Thursday, and it is the same thing with a practical example. I try to be slower. Okay. Any other question? Yeah.
I try to use another function, this create table. I don't know if it works in the same way, but it seems like to change the rows and columns in the order, maybe.
Oh, okay, maybe. I never used create table. Is a function into R that can read from a text file.
Yes.
Okay, this is a useful information. You can take a note. So maybe this is a way to directly create the matrix from the text file by avoiding this. And by the way, it is really possible. I'm not an expert of R, so it's really possible that you may find quicker solutions. And if you find quicker solutions, just let us know. Okay. Good. Any other question? Okay. So don't forget RStudio to install it. Another thing that I want to ask you to install, this year, I decided it's time to work with the students also with Python, which is another free software to make codes, computation, etc. So my aim is to stick on R, because I know it better, but I also would like to try to work in parallel with Python. The nice thing is that I'm not a Python user, so I need to learn. So I think it's nice that we try to learn together, okay? But in order to be able to work together with Python, you need to install it, okay? So maybe that you already have it, because in Mac, I think it's already included. Otherwise, in Windows, you just have to do this. And Unix is already included, Linux. So if you are a Linux user, probably no one. It's already included. And I think also Mac. So here, you can write in find Python. Okay, it's already installed here. Otherwise, if it's not installed, so let me try to execute it. Okay, here is Python. No, it's not installed. So you have to get this one, Python Software Foundation, get it. I just show you, it is very easy. And then it is automatically installed. And it looks like R, the console of R, but the commands are different. Not much different, but it's a little bit different. Now it's very slow, so we don't wait, okay? Just, okay, it's not very slow. And just install it on your PC, please, so we can work together with this. And as I said, when you start it, it's like R. Let me see, I think it's already installed. Okay, so let me see where it is. Should be somewhere here. Python, okay. You see, it's a console-like R, identical. And then you can find 2 + 2, identical. But the commands, unfortunately, are a bit different. But the concept is the same. So we just have to learn. We can learn them in parallel, okay? No, we don't work into Python now. Why Python besides R? Because it's one more platform. And according to my PhD students, who are more experienced than me in using these softwares, they say that when they have to create very nice figures or make sophisticated computations, they use either R or Python, depending on what they want to do. And therefore, they told me, you absolutely need that because it is the future. So given that when I was told it is the future, okay, that's fine, I will learn it. But I'm not able right now to make more than 2 + 2. Okay, so I think this is very nice because maybe that some of you already know it, so we can really work together, okay? I try to anticipate. So on Thursday, if I will do something, of course, I will try to anticipate. The first thing that I want to learn is precisely this one, how to upload data, okay? Maybe there is a scan. Let me see if the help, it's no, I think here it's help. And let's see, help scan. Okay, scan is not defined. So scan is not the same function. So it must be something different, okay? And there are several tutorials. If you go to Python that I think maybe org, let's see. I'm not sure, I'm just, okay. You see, there is documentation, docs, beginner's guide. Beginner's guide, I had a look, it's nice. And so there is a lot of documentation. Let me just remove this, okay. And so here it is, okay. Don't be annoyed because it is indeed the future. Okay, my students also told me the future is also ChatGPT. I think they are right. On the other hand, I tried it a little bit, and I think that it is very useful for many things. First of all, be careful of getting the text because maybe plagiarism. You know, they have already been sued by, I think, by the Guardian or New York Times because ChatGPT tends to repeat what was read in any website, including those that are require the subscription. because they may have the subscription. So be careful when you cut and paste from ChatGPT, because it may be dangerous. I think I already mentioned to you that if when you prepare your final year project, your thesis, you get trapped into plagiarism, the punishment is really heavy. I know of some students that have been, thrown out by the University of Bologna with a ban, a lifetime ban, and the degree, of course, taken back. So try to be very careful about plagiarism. And when we write papers, scientific papers, we are really told by publisher, be careful, because it's a crime. Okay, it's a crime. So one has to be very careful. And I think that ChatGPT lacks creativity. So it is a bit hard to think that one can be innovative without creativity. It's hard to believe that you can be innovative by just putting together what is putting together, even in a very nice manner, with a very nice synthesis, what is found on the web. On the other hand, to find the information to support your creativity, I agree, it's really great. Okay, let's go out from here. And then let's go back to where is the web, the browser. I think I closed it. Just 1 second. Firefox. Okay, let me go back to my website. Okay. Climate change adaptation. Okay, so we finished the climate change problem. Okay, let's be a little bit more narrative in this lecture, which I will not do completely. I will not discuss completely. Let me just click on here. This is an introduction and a discussion about sustainability. So I leave part of this lecture to you for autonomous study, because it's mainly a narrative, and I will focus your attention during the lecture only on the keys of this lecture, of this web page. Okay, I think it is an interesting read, and by the way, read it, because you may get some questions from this lecture in the quiz. Okay, and also in the oral. And so I have a look at the text, and please study it. Okay, I will draw your attention on some part of it, and I will not use the PowerPoint. The PowerPoint that you find at the bottom of the page is too much extended. It includes also some other things which are not necessary. So just refer to the web page. Okay. So there is the section 2. The section 1 is an introduction, and we already discussed what are the threats to sustainable development. Okay, so increasing demand of energy, increasing CO2 emissions. So this is something that you can read. And then section 2 focuses on the global forums on environment and sustainability. I want to say a few things about these things. Let me just change the camera, because I think that you are aware of the many forums that have been activated at the international level over climate sustainability, like the Rio conference that is held of the United Nations, that is held every 10 years, and the Kyoto Protocol, the Paris conference of 2015, the COP conference on climate change, COP. And let's try to understand how these forums have been activated. First of all, they are a recent invention. And the first one was, let me just find it out. The first one was okay, was in 1972. I just have to find it. Okay, let me just find 1972. Okay, perfect. The United Nations Conference on the Human Environment. It has been the first international conference on the global dimension of environmental problems. Okay, and it started from the awareness that water resources were under threat. water resources were depleting. Keep in mind that the Yellow River, the downstream part of the Yellow River, dried up for the first time in 1972, and dried up for the water withdrawal upstream. Okay, so basically, in the 70s of the past centuries, people and governments realized that water resources at the global level were suffering, and therefore they activated this conference. It was the first international conference, again, of the United Nations on the global dimension of environmental problems. And you can find also on Wikipedia something more on that, okay? It's not important that you learn the details. It's just the concept is that concerns about environment and the sustainability began the first international conference 50 years ago. So it's a recent, as I said, a recent invention, or let's say a recent awareness, okay? And then since then, there were several conferences. The most important ones, and it's not, please don't learn by memory the name of the conferences. It's, you will not find any question related to that. The most important one them are in 1992, the United Nations Conference on Environment and Development, also called as the Rio de Janeiro Earth Summit, the Rio Summit, the Rio Conference, etc. And it was held in 1992 together with another conference in Dublin, same here, that focused the Dublin Conference on water resources, and the Rio Conference was more general, okay? And it was attended by more than 100 heads of states. I think the plural in states here is my mistake. Heads of state, without the final S in state. Okay, another significant step was in 2002, and it was another conference after 10 years. It is after the Rio conference. It is also called the Rio Plus 10, and then the Rio Plus 20, and then the Kyoto Protocol and the Paris Agreement. The Paris Agreement that set the targets of global warming that ideally we don't want to trespass, okay? And so these are the products of these conferences, the Rio Declaration, Agenda 21. Agenda 21 is quite actual, and Agenda 21 is an action plan of the United Nations with regard to sustainable development. It's a product of the Earth Summit, so in Rio de Janeiro. And basically here there is first introduction of the targets let's see, the targets that humanity wants to meet for sustainable development. And part of Agenda 21 are, I close this, are the Sustainable Development Goals. One second, Sustainable Development Goals, which I think you already know. Development. I think, just 1 second, I will get it. Ah, here they are. Okay, here they are. These goals are divided, each one of them, into targets. Okay, and these are goals that ideally they are part of the, you see, of the Agenda 21, which is also called the 2030 Agenda. And ideally, we should meet them by 2030. And 2030 is very close, you understand. But in 2015, it was set like a 15-year target. And with the awareness that not all of them can be achieved, but still they are a term of reference. And they are also criticized from one side, because you understand that reaching these goals, I mean, requires an effort that implies a political commitment, but it also implies a social cost. And, the political commitment, it is sometimes slowed down by the awareness of the social cost. The social cost implies in turn a cost in terms of popularity of political administrations, lack of consensus, but it also implies, and this is more important, a cost for people. And the cost for people, of course, there is the risk that is higher for the countries with low gross domestic product, lower gross domestic product. As we will see in some details, I mean, the large amount of CO2 emissions is released by countries with a very high gross domestic product. It's uneven. I mean, the countries with the lower gross domestic product, with less resources, don't emit too much. And but when we set up a global agenda, a global commitment to reduce emissions, it's clear that it's more difficult to reach for the countries that already have a low emission. For countries that are emitting a lot, the social cost can be met in a easier manner. And therefore, these goals are also criticized because some people say, and this is something that to some extent is reasonable, some people say that they were set up by referring to the condition of the rich world, not of the poor world. So ideally, what we should do is not to put any limitation on the poorest countries, on the poorer countries, and we should concentrate the limitation on the countries that release the most of the CO2 emissions. On the other hand, you understand that setting a global target it's not easy, and if this global target is basically creating disparity, it becomes close to impossible. So basically, this is seen by some as an utopia, something that cannot be reached, and basically fixing targets that cannot be met implies an increase of tensions, an increase of international tensions, which is what we want to avoid, because international tensions in turn have an impact on sustainable development. In order to reach a sustainable development and in order to reach an effective climate policy, you understand that ideally we should get rid of any international tension. When there are wars, you understand, it's the CO2 emissions explode for many reasons. And when basically some people say when international targets, when global targets are set up, one should keep in mind what is the impact in terms also of international tension, political tension, etc. And some people are convinced that setting up these climate policies, setting up these sustainable development goals has increased the international tension rather than decreasing it. And indeed, if you look at the recent history, you can see some demonstration that this is true, like energy dependence from some countries by other countries that has been reached because some countries wanted to use natural gas in order to decrease the CO2 emissions, so creating energy dependence. And energy dependence in turn created a huge social cost for people. You may remember the increase of the price of energy that we experienced after the onset of the war between Russia and Ukraine. So indeed, I mean, what I wanted to tell you is that it's not simple. It looks like a very nice narrative, sustainable development and the reduction of CO2 emissions, but actually there are a lot of socioeconomic implications and political implications that make this target really something delicate, sensitive, and not so nice overall. That being said, it's clear that we need targets. We need to care for environment. We need to care for sustainability. Okay, this is why I think the history of these conferences is interesting. Basically, these conferences were promoted when globalization arose, when liberalism, economic liberalism, got into play, and then they are a bit are a bit how to say, in a difficult situation in this period where economic liberalism has proved to be to fail. Okay, so basically here there is a pictorial representation of the fact that economy and society are conditioned by the environment. And I think it is nice, this graph, which shows the crossing of environment and social dynamics and economic dynamics, and basically look at the intersection. I think the intersections are interesting. The intersection between what is environmentally sustainable and socially sustainable is bearable, and what is the intersection between social sustainability and economic sustainability means identifies the area of the equitable. The sustainable area is given by the crossing of the three components: environmental dynamics, social dynamics, and economic dynamics. Do you have any question on this? Okay, we can skip the role of science and engineering because this is what we already discussed. And let me now introduce an interesting discussion on which is very actual today. What kind of approach should we follow for reaching sustainable development, for also climate change adaptation? And in this case, it's called risk management, but you can apply the same question. You can ask the same question for any problem related to environment, society, and economy. So what kind of approach? There is the predominant scientific approach in solving socio-environmental economic problem is to start from predictions, from models. And in fact, we talked about climate models, for instance. So basically, we make models, economic models, socio-economic models, and environmental models, and we make a prediction of the future. And then from the prediction of the future, we test policies, solutions. We test design projects basing on predictions. Basically, I think there is a sketch here. You see future society, predicted climate. In this case, it makes reference to water resources and flood analysis, flood risk analysis. So it talks about runoff, which means river flow, inundation, and then solutions. What is indicated here with people, it's solutions. So benefit for people, okay? And this is what is called the top-down approach because it starts from a prediction, okay? Now, there is the problem with this approach that solutions come at the last position. And there is also the problem that predictions are uncertain. So in order to cope with uncertainty, a usual approach in engineering is to introduce a safety factor. When there is large uncertainty, we adopt large safe factors, like, to make an example for water resources and flooding, I need a dam in order to store water resources and get protected from flooding. So I start with a model predicting dynamics of water resources in the future and flood risk. The model is uncertain, I'm aware of that. So if I get a storage of the dam, which is, say, 10, in order to make sure that I get protected against uncertainty, I suggest a storage of 15, and this is a safety factor of 1.5, which is the safety factor that is normally adopted in engineering. This is the usual way of engineers to cope with uncertainty, and it's very classical. It's a practice that is very old, it's centuries old, meaning that engineers have been always used, like any of us, to cope with uncertainty. They have been always aware of uncertainty, and they use the safety factor, which is typically 1.5, which is a lot. It's a lot. I need 10. Okay, let me make the design project for 15. So it's 1.5, 50% more. It's really a lot. Okay, and this is the usual way engineers cope with uncertainty. And if they realize that uncertainty is really large, something that unmanageable, sometimes engineers introduce a safety factor of 2. Like, I need 10, okay, the model says 10, okay, let's go with 20, okay? And the same we do every day in our life. I mean, when you have to fill up the car, usually if you don't get to the last kilometer with the tank, the fuel tank that is empty, you put more fuel. And usually, if you think of it, the safety factor that you use is similar to that of the engineers. Usually you want to have a safety factor of 1.5. The reserve in the car, when it gets really like tank empty, it's not empty. You have usually 50 kilometers more, okay? It's a safety factor. Okay, but there is one problem here. If you get uncertainty over uncertainty, like in this case, you have a climate prediction and you account for uncertainty, but then there is a runoff prediction, and then there is an inundation prediction, and at any step you introduce safety factor. So very often in climate change adaptation, you end up with projects that are unsustainable, cannot be done because they are too costly and they are too invasive in the environment. Because you understand, we already said this, a dam has an impact. If you get a dam of twice the size, the impact is more than twice in terms of environmental sustainability. So this is one of the reasons why usually when we talk about climate actions, when we devise climate actions, we don't materialize them because they are unsustainable. And therefore, people precisely in climate science started to think about alternatives. And the alternative may be the bottom-up approach. And the bottom-up, you start from the solutions. So you are aware that there is a problem in the current climate, okay? In the current situation, we have a problem, like the flooding in the Romagna region. This is a problem. We don't want to get another flood. Okay, let's determine the size of the intervention that we need to solve the current problem without caring of the future, of the predictions. Let's solve the current problem. Let's focus on current needs for people. Okay, let's focus on the solution. First question, is it sustainable? In many cases, we get an answer of no, because like in the Romagna region, we need the detention basins, okay? To store excess water from rivers, but we don't have the space. So it is a big problem. So first question is it sustainable? It is doable. Okay, if it is doable, then let's do it. If it's not sustainable, we need to find another solution. And when we found a solution, then we can test the solution against the prediction of future climate. So we can test the solution against the predictions, whatever the problem is, okay? The same for socioeconomic model. When I talk about water demands and I make a prediction of water demands into the future, usually we get a sharp increase of water demands in the future because the per capita demand is increasing. The population is not clear. In some part of Italy is decreasing, in other part is increasing, but usually you get an increase of water demands. And if you want to design a water supply project in order to meet these future demands, very often it's hardly sustainable because it means that you have to take a lot of water from the environment. So the proposed solution is, okay, let's focus on the areas where water is already scarce. Let's solve the current problem, and then let's test the solution against the socioeconomic development by taking into account uncertainty. So your question may be, what happens if the proposed solution fails the test against the future, okay, against the prediction? Then we can manage a solution that is flexible. And in many cases, it's possible. So in many cases, instead of building a huge dam, you can build a small dam. And then later on, if you really need a second one, you build the huge dam, like they did in Aswan on the Nile River. They first built a small dam, and then a little bit downstream, they built a second one that flooded the whole dam, which is no problem. And they used a flexible approach. So you can use flexibility and leave to future generation the task of testing with respect to the future. So this is the bottom-up approach. It is criticized like the top-down, and it is criticized because it is the analysis of the current problems. It's also something that is not easy because you have to set priorities, and sometimes basically to set these priorities, it's also a political problem. So it is more urgent to concentrate the funding on the one region, or it's more urgent to adapt the buildings in Italy against earthquakes. And you understand, it's something that it's not easy, and therefore it doesn't solve really the problem. This is the criticism that is directed towards this bottom-up approach. But still, I think it is important to concentrate on the current time because indeed predictions are uncertain. And it is important that we take climate actions, climate adaptation, mitigation. And even if the solutions are not really final solutions, I don't think it is a problem. I would be happy anyway if the solution was a first step. And this is what the bottom-up approach proposes. Let's move forward step by step. Any question? Okay, now I want, in order to close this discussion, to focus on some particular issues related to sustainability. First of all, I didn't give the definition of sustainability. Let me just focus on it. And here it is. Okay, I think it is here. Okay. First of all, when the sustainable development was defined, just let me check if everything is fine with the recording, and yeah, because I got a sound, an alarm I wanted to check. Okay, so sustainable development was defined in the 80s and the beginning of the 90s of the past century at the international level. Basically, in 1983, the United Nations activated a commission called the Brundtland Commission, from the name of the president, more formally, the World Commission on Environment and Development, which developed a definition, proposed a definition of sustainable development. I think you already need it, but just fix it in your mind. Sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Okay, keep it in mind. It's basically solve current problems, but think also of future generations. Okay, and the two key concepts here are the needs and in particular the essential needs of world's poor, okay, and the idea of limitations. Keep in mind that the limitations to development is something that we understood only recently, okay? And I mean, there is a limit. There is a limit in the sense that I mean, we are not sure that present and future needs can be met. So this is the limit, okay? Okay, as I said, some particular issues. The water, food, energy nexus. Okay, so what is the water, food, energy nexus? So development means ensuring water for people. It means ensuring energy, ensuring food. And these are strictly related because the state of water resources depend largely on irrigation and which is the main use. So the main use of water at the global level, 70% of the fresh water that we use is dedicated to irrigation. And irrigation means food production, okay? There is also the problem of energy production, which is produced, as we will see, with a large amount with water, renewable energy. The largest part of renewable electricity that we produced is hydropower, is through water. Therefore, water is essential for life. It's essential for food production. It's essential for energy production, but water is limited. And the multiple use of water for both irrigation and energy production is not always possible. So in some of the cases, we have to set priorities. So use water for food production or using water for energy production, and it's renewable energy. And therefore, there is a strict relation also with the climate change. And this nexus, this link between water, food, energy is a research field that emerged like 15 years ago, okay, and it's very popular. So how to find the best compromise through bottom-up approach, scenario development, which means prediction, and what we really believe is important is the dialogue with stakeholders. On the other hand, also the dialogue with stakeholders is a nice story. It's very nice to say we need to talk with stakeholders, we need transparency, which is indeed a nice narrative. On the other hand, the dialogue with stakeholders is extremely difficult because stakeholders have different views. And therefore, one of the most important roles for a policymaker and for engineers and scientists today is communication. Communication with stakeholders and ability to reach a compromise. But we realize that it's indeed very difficult because when you put all the needs together, of course, I have some experience in water resources. When you build a dam, when it's time to decide whether the dam capacity should be reserved for flood protection or irrigation, it becomes a very complicated discussion. And the discussion, in some of the cases, becomes so complicated that the result is once again no action. When you fail in reaching an agreement with stakeholders, very often the result is no action. So the debate basically is, should we prefer a top-down approach? There is a hierarchy of decision. There is an authority that decides. This is a version of the top-down approach in policy making, okay? There is an authority that decides. This is the top-down approach, and some of the stakeholders will be unhappy. Anyway, the authority has the responsibility to take the best decision for the common good. Or should we start with the consultation of stakeholders? stakeholders get their discussion, and then the authority at the end decides, but basing on the discussion with stakeholders. So what is the best solution? Difficult to have a say on this, difficult to say. What we do typically is that in order to resolve the dialogue with the stakeholders in a bottom-up approach, we had to introduce decision support systems, which are like unbiased and technical ways to reach the best compromise. Decision support system means decision theory. This is why we dedicate in this course a couple of lectures to decision theory, which is something that usually the students hate because it's very mathematical, very statistical, in order to reach an unbiased decision, you have to remove in a way creativity and make a reasoning basing on let's say limit creativity, not remove it, because you will see that in decision theory there is still room for some creativity. But you have also to make sure that any conclusion is objective, and objectivity is reached with statistical analysis of the different opinions. And it's a real complication, requires additional resources, and it's not always successful. So today, I'm personally convinced that the dialogue with stakeholders is something that it has been a very nice achievement. It should be kept. On the other hand, I personally experienced that it's really tough, really tough. And there are some discussions that are really sensitive. And, sometimes my usual way of action is I tend to make myself available. So when people want to discuss, okay, let's discuss. But in some of the cases, I was really exhausted, and in some cases also a bit concerned, because when you discuss with people that get very angry, sometimes I felt like not unsecure, but a bit challenged, let's say. And it's really not easy when the topic becomes very sensitive. I also had discussion on waste treatment. Waste treatment landfills, tough, really tough. Okay, but the water food energy nexus, it's an important field of research. I would say that it is something that is still very narrative. It's not really evolved into some technical development, which is something that I really look for, because technical means solutions, means action. We need methodology, we need technical guidelines to move forward. And yeah, this discussion, as it often happens when you cross engineering with social sciences, it often happens that you end up with narratives that have little technical content. And this is not really good, because it means that solutions are still far away. Okay, and then energy production. I want to show you some graphs, because energy is the real problem today. Okay, when we talk about climate change, when we talk, it's energy. And let's see in where can I find it? The split of the CO2 emissions. Let's where CO2 emission come from. Okay, our world in data. So our world in data basically is here it is. You already know the website. We already browsed it, and there is a section on CO2 emissions. Let's see, energy and environment. It's not here. Just 1 second. Should be here. Let me see. Outdoor, indoor, clean water. Okay, let me see. Energy. No, sorry. It's not here. Adaptation innovation. There must be a section on. Okay, let me see. Climate change. Okay, CO2 and greenhouse gas emissions. Sorry, I didn't see it. Okay. So here you can see, oh, this is temperature. Okay. Let's start to see some graph. Here you see CO2 emissions per capita, and you get an idea of what I mentioned before. And still, you can see, first of all, a decrease for almost all of the countries in the recent years. Here, this graph is up to 2022. It's very updated, okay? And but you see that the United States are still the highest emitter per capita. These are emissions per capita, okay, which is what you should look at, okay? Because of course, I think that if you look at the global emissions, probably China is the main emitter, but in terms of per capita, you see that it's increasing, China, but it's still quite low. And if you put Italy here, you see that Italy is not a huge emitter. Still, it's more than United Kingdom. And if you put, to get an idea of some other important countries, we can put Russia, and you see that it's quite high, but it's still above, below the United States and above China. Okay, this is global CO2 emissions. And now let me see. Okay, here, this is what I wanted to look at, emissions by sector, okay? Where do greenhouse gases come from? This is interesting. Okay, let me decrease it. So energy, 73%. So you understand, energy is the key, okay? So energy production is 70% of the CO2 emissions. And then we have agriculture, almost 20%. The remaining ones are really low. Industry, waste, it's low. In energy, there is also transport. Look at the split of energy, okay? So there is energy in agriculture, energy production, unallocated full burn of fossil fuels, energy used in building, transport, and energy used in industry. Energy means not electricity. Energy includes electricity, but it's much more than electricity. So when we put fuel into the car, it's energy production, okay? So you understand, energy means it's not only electricity. We will see electricity then. I think it is somewhere here. Let me see. Energy used in industry. Let me just, aviation shipping. I don't think there is electricity here. Because it is divided by sector, not by type of energy production, okay? So energy is really the great emitter. And here it is now, electricity and heat. Here there is greenhouse gas emission by sector. Let me just enlarge it. Okay, electricity and heat is the main contribution, and then there is transport, manufacturing and construction, agriculture, and that's it. Aviation is very low. So sometimes, you know, planes, international flights, it's very low, aviation. And this is something that it's obvious, you understand. And if you compare with cars, aviation's the number of planes, the flights are not really dominant, okay? And electricity, it is something that is stimulating a lot of reflections, because sometimes we say better to take the train, but the train is moved by electrical energy, and electricity production, unfortunately, requires CO2 emissions. And then, of course, what we say is renewable. We have to resort to renewable. So now the next question is, what is the proportion of renewable energy? But because otherwise, you understand, it's useless that I take the train if electricity, production of electricity is the main emitter. And of course, there is also a message that you deliver when you take an action. And the message is important. I'm not saying that we should encourage the use of the plane with respect to the train. Absolutely. It's also important, the message. The message is that indeed the train is something that is more environmentally sustainable with respect to a plane for many reasons. On the other hand, it's clear that it doesn't solve the problem. We don't solve the problem of the CO2 emission, the specific problem of the CO2 emission, if we take the train. And the problem would be solved if electricity was generated by renewable. Okay, so let's look at the percentage of renewable. I think it's already in my website. It's a bit update. It is outdated because it is 2010. I'm sure that in our world in data there is a similar graph. And so if you look at the total world energy consumption by source, fossil fuels are still around the 70, I think 75 now. And the renewables now are up to the 20%. This is still energy, it's not electricity, okay? And nuclear is 2%, okay? And the renewables, you see that there is a large contribution of biomass heat, and there is a significant contribution of hydropower. When we look at electricity, the contribution of hydropower goes up, okay? But it's still after the biomass heat, there is hydropower. And if you look at the contribution of solar energy, wind power, they are still very, very low. I mean, wind power is increasing, but it's 1/6 of hydropower. And in the total contribution is negligible. We are not considering here, this is a static picture, we are not considering also the problem of variability of these energy sources. Hydropower has the nice feature that can be regulated. So we can produce hydropower when it's available. The same is not true for wind power, okay, or for solar power. Now, energy production by countries, it's still heterogeneous. And let me just look at electricity. I think I have a graph here. No. So let's look at our world in data. Topic, energy and environment. CO2 is also here. And let me see, renewable energy. Energy. Okay, let's see, renewable energy. This is updated, of course. Okay. This is electricity. This is the graph I was looking for. So if we look at electricity, hydropower is the main contribution. This is global, okay? And then you can select by countries. Here, as usual in our world in data, you can select by countries. So hydropower, wind, solar, and other renewables. So the great contribution is by hydropower. It should be something like 20%. Let me see. It's more than that, actually, at the global level. It's about 50% in terms of electricity. Just let me check. Yes, it's about 50%. And probably my reference to 20% was for Italy. We can check. And then there is wind, and as I said, solar and other renewables. This is renewable, but still, if you look at the generation of electricity, I think, let me see in the topics. Okay, energy. Energy, electricity. I think should be this one. Okay, here you can see where electricity coming from, and here you can see the contribution of renewables, and unfortunately is still very small. And we have, just 1 second, I need to admit a person. You see coal is the main contribution, gas, natural gas, and then oil, still CO2 emissions, nuclear, hydropower, and then there is the other contributions. Okay, here there is other renewables, not really, it's not only renewables. So other renewables is a small contribution, but here you see that there are some of them that are renewable, and gas doesn't emit CO2 emissions, and hydropower is renewable, and then there is wind, solar, etc., and bioenergy. So you know that it's a big question. How can we remove the contribution of the coal, and which is a great contribution? It's almost half of our electricity production, and it's more than half of total energy production. So how to remove the contribution of the coal? Because still, when we take the train, half of the energy to move the train comes from coal. And it's not an easy question, because you know that there are some different possible solutions. One possible solution is the nuclear energy, which is becoming greener today, and also less risky today. But still, there is a lot of discussion on nuclear energy. Personally, I am convinced that the only way to get carbon neutral is to use nuclear energy, because nuclear energy indeed can be expanded a lot. While with the renewables, I think for hydropower, there is little room for expansion, and there is room for expansion for solar and wind energy. But you know, the environmental impact of solar energy production and wind farms, solar farms and wind farms, is relevant. And if you look at the web, at the literature on the environmental impact of these two solutions, and also hydropower, of course, it's indeed a huge impact. Of course, so what is the solution? Is nuclear to sustainability? This is a difficult question. But it seems that probably the nuclear option is gaining attention, because probably it's the only way if you want to move away from fossil fuels. Any question on this? Okay, last thing that I want to say on this is this figure that I want to discuss with you. Let me put it on the screen. Okay. So what is the water footprint? The water footprint is the volume of water that is needed for a country for the production of goods and services that are consumed within that country. So this is a new concept. It's not really new. It was introduced about 20 years ago, when we became aware that countries that were suffering from water resources availability decided to import food. So they basically didn't have enough water to produce food internally, and therefore they decided to import food. And this was made possible by the end of the Cold War and the start of the globalization. So when globalization started after 1989, after the Berlin Wall was demolished, globalization, international trade became easier. Today, it's a little bit compromised in the past 10 years, but at that time, really, with the advent of economic liberalism and the advent of globalization, the international trade increased a lot. So several countries decided to use this international trade in order to compensate for their limited food production. But in doing that, it's clear that, especially if you import food from the countries with lower gross domestic product, this may be detrimental to those countries, because those countries also need food. Think of Africa, they need food. And if you import food because you give money, so I mean, with the power of economic dominance of more powerful countries, you basically take the food that they would need, and in doing that, you use their land and their water. So the scientific community introduced the concept of the water footprint as including the volume of water that a country uses for the production of goods that are consumed by that country. So the water footprints includes the internal use, but it also includes the use that was done in another country to produce the food that is eaten by the importing country. This was also termed the virtual water trade. So water cannot be moved physically. But if you move goods that are water demanding, you basically obtain the same result. If you move food, it's the same result as moving water. And there would be nothing wrong if you move the food that is in excess in a region, in a country, to bring it towards the countries that are suffering from lack of food. But actually, we realized that it was the opposite that was taking place. So countries already suffering for lack of food were exporting food to compensate the high demand of food by high demand of water in this case, because it's not only food, high demand of water from countries with a higher level of welfare, higher gross domestic product, so countries that could pay for these goods. And you can see the resulting map, okay? In dark blue, you see the countries with the largest use of water and water footprint. And with the light blue, you see the countries with the lower use. And you can clearly recognize that there is a disparity. You can clearly recognize countries that have a too low water footprint. It means that they are using too limited amount of water. And this is, I think, it's an interesting picture. And what is even more interesting is to look at the volume of water that is needed to produce some goods. Let me anticipate first the figure on the left of the drops. You see on the left there are 100 drops, and these drops represent the total amount of water. So if you represent the total amount of water with 100 drops, you see that only 3 drops are given by fresh water. And this is the pictorial of the reality that we know that 97% of the water of the earth is salted, so fresh water is only 3%. Still, there is enough water to feed humanity, even in a prediction of increased demographic, increased population. I mean, the 3% of fresh water is sufficient for everybody, even if we assume that the global population will become twice of that, 3 times of that. The problem is that the distribution is not is uneven, okay? Uneven in terms of time and space, and therefore and water cannot be moved easily because it's heavy. So the virtual water trade may be a good way to compensate. The virtual water trade may be the way to compensate for the uneven distribution of water. But if we look at the current footprint, the map, you see that the distribution is still uneven. Of these 3 drops of fresh water, only 1 drop can be used by humans. The other 2 drops are glaciers, ice caps. Still, there would be enough water. Okay. Another interesting information given by this picture: 70% of existing fresh water is withdrawn for irrigation in agriculture. Okay. These are the countries, the countries most dependent on water imports: Bahrain, Kuwait, Malta, Netherlands, etc. And the highest water footprint per capita: United States, Greece, Malaysia, Italy, Thailand. Now, let me just finish with this figure and then we make the break. Water footprint of different foods. This is extremely interesting. Okay. So 1 kilo of chocolate requires 24,000 liters. 1 kilo of beef, 15,000. 1 kilo of olives, 4,000 liters. Just to give you an idea, 15,000 liters, how many cubic meters are? Learn this. 1 cubic meter is 1,000 liters. So it's 15 cubic meters of water to produce 1 kilo. It is amazing. You may say impossible. Okay, let me just move forward and I will explain better. 1 kilo of sugar, 1,500. 1 cup of coffee, 140 liters. Okay, so I attended once. I presented this figure at discussion in a Reddit discussion. Do you know Reddit is the website that promotes discussion on topical issue at international level? And when I showed this picture, there was a farmer that intervened in the discussion, and they said, "Farmer here, I can't believe that. I have 100 cows, and I can tell you that I don't consume all the water that you are claiming here." And I replied by saying, "Okay, but if you look just at the bill of the water supply, it's not really what it's not really giving you the right picture, because there is also water for irrigation and the rainwater that you don't include in the bill, but you are feeding the cows with grass, and to produce a cubic meter of dry grass, really you need a lot of water, and some of this water may be coming from rain, but still you need it." And when I talk about global water availability, I also talking about the rain. It's not only the water that comes from the tap. And also you are probably not counting all the water that you need in order to produce the fertilizers that you need to give over the fields. And these are studies that are well documented. There are scientific papers. And of course, when you talk about rain, it's a lot of water. So it's not surprising that it's so huge, the amount of water that is involved. But still, let's think that, the meat, we know that the meat is CO2, means CO2 emissions and water use. The countries with more renewable water resources are those that you can see here: Brazil, Russia, USA, China, Indonesia. And keep into account that about today, I would say that 4 billion people, so almost half of the global population, is facing water stress or scarcity. Okay, that's it. Some of these numbers, the easiest one to remember, you may find some question in the quiz, okay? The easiest numbers. You don't have to remember the number of water footprint of the United States, okay? But the 70%, yeah, maybe. 90% of 97% of water is salted. 97, remember the number. These are easy to remember, okay? I think that we are almost done, but let's make the break now. So let's meet again at 11:05. Questions? Okay, so okay, let me just make a couple of final considerations on the water footprint. There are some other figures on the distribution of blue and green water footprint. Green means for irrigation, blue means water footprint from surface water, and gray means water footprint from groundwater resources, etc. And I think I leave to you the analysis of these figures, which deliver some additional information, but are not really relevant to the general discussion that we had. What is interesting is to look at this. Let me just open it in another. This is the global water footprint by sector. And it's what you can see here is the internal water footprint is 78% at the global level. Agricultural products are 72%. It's in line with the percentage of 70% that I indicated to you earlier. The external water footprint is given by the imported goods is 22%, and 20% are agricultural products and 2% are industrial products. What you can see from the composition of these two figures is that food production, agricultural products, is playing the key role, both in terms of internal water footprint and imported goods, external water footprint. And then here you can see the contribution of, at the global level, of industrial products and the domestic products. Okay. These are contribution, as you can see here, 2011. This is a very recent field. Okay. And I think that that's it. Do you have any specific question related to this? So what we discussed today is sustainability and international development of the concept and specific issues related to sustainability, water use in terms of internal water footprint and external water footprint, and the water food energy nexus. By the way, I got a question by one of you, and the question is related to the mention that I made to my personal experiences, because I mentioned to you that I was involved in some projects related to sustainable use of water, mainly water. I was also involved, as I mentioned, in waste treatment, but mainly my experience is related to water resources. And if you are interested to know more, I can deliver in one lecture a presentation on a specific project. This is fine. The only condition that I pose, I don't want to be the first one. So I invited you to deliver presentations on a topic of your interest, and very short one. And I want to reiterate, to repeat this invitation. So if you have an idea, a case study to present, and you don't have to substitute me in lecturing, but if you have something related to sustainability, to climate change, specific problems, case studies, or something that you searched on the web and want to present because you think it's interesting, please do send me an email and we start booking these presentations. And the requirement is just that the presentations contain some technical detail. And the requirement is that the time of the presentation should be between 5 and 8 minutes, ideally 8 slides, including the title. And I would prefer that is delivered individually. But if you want to put together a group, no more than 3, and you understand that it's a bit difficult if you are 3, because with a total time of 8 minutes, shifting the speaker becomes a bit more complicated. So my suggestion is try to work alone or at most in 2 persons. And then if you start, I will follow up. Okay, and I will take some more, because in order to present a project, a full project, I need like 20 minutes. But I am willing to deliver a presentation on a specific project I dealt with. Okay, keep in mind that my presentation, if I deliver this presentation, is not a matter for the exam, because it will be technical, but not really something that you need to learn by memory. It's just something to inspire you. Okay, so I'm willing to, but I don't want to be the first. So this is my way to stimulate you to deliver presentations. It will make also the lectures more entertaining, you know, if we have some discussion, otherwise, if I only speak, it becomes boring. Okay, but I think we can move to the next one, lecture, if you don't have any question. I anticipate that the next lecture, meaning the next lecture note, which we discuss a bit today, but essentially we will discuss it next week, maybe something on Thursday, and then next week, is more technical. Today it was mainly narrative. Okay. Don't assume that narrative means no questions at the exam. It's not. This is not the meaning of narrative. Okay, it's just the fact that, you know, some of the lectures are technical, some others are narrative, but they deliver information anyway. Sometimes it's easier to remember the technical information than the narrative information. So try to distill what you need for enriching your background at the best, and for passing the exam with the best of your reward. Okay, so back, risk-based adaptation design. This is the next one. 1 second for the upload. So basically we are getting here, let me see if there is a PowerPoint. I don't think so, but actually I don't need it. Okay. And we are getting here into the core of our course. This is a lecture which contains some information that is extremely important, and because it's the basis for designing projects. Okay, and given that it's important, of course, it's also a source of questions at the exam. And we are getting here into what I said, the design phase, which is not only a task for engineers. Absolutely, of course, the engineer is in charge of making the technical part of it. So if there is an infrastructure to size, and if there is some theory or involved of structural mechanics, hydraulics, the engineers once again have the technical task related to the design. But the general design is also a matter for policymakers, for social scientists, because here we get into the question, what kind of solution should I adopt? So it's also a matter of taking a decision. And there are several ways to take these decisions. And several ways, because there are several branches of decision theory which differ among each other based on the criteria that you follow. So the decision may be taken by looking at the economic benefit, for instance. And this is a task for economists. So you make a cost-benefit analysis, and then you take your decision, and then you design your solution. Or, like in the case of this lecture, you may base your decision on a risk assessment, risk analysis. And given that we deal with climate change, this is the usual way that is followed. So climate change, you know, is frequently discussed for the risks that may come from climate change. And these risks are, most of them, delivered by the so-called natural hazards. where natural means that they come from environment, from natural processes. There is an interesting discussion nowadays because some people don't want to call them natural hazards anymore, because natural may induce the feeling that they are not human induced. Let's keep the definition, the terminology natural hazards, with the agreement between us that the natural stands for related to the environment, to nature, not their origin, okay, not their cause. It's not necessarily a natural cause. Maybe natural, but we mean natural in terms of environment. There is, these natural hazards, what we call natural hazards. Let me give you some examples. Droughts, floods, earthquake is a natural hazard. Is considered to be a natural hazard. Windstorms, heat waves, hurricanes, these are natural, these are examples of natural hazard. Okay. Most of them are related to climate change. So let's say that climate change has implications on most of them. I say most because there is indeed today the belief, an increasing belief, that climate change is affecting all of them, including earthquakes. You understand? Yeah, it's possible. You understand that the groundwater flow may be influential on the earthquakes, and therefore groundwater flow is related to climate. On the other hand, let's be clear about the priorities, about the implications. So it's clear what can be the implication of climate change for floods and droughts. It's less clear what the implication may be for earthquakes or for other hazards, like which are not natural hazards, but there are other relevant hazards that are related to terrorism, to international socioeconomic dynamics. These are not in the realm, in the pool of the natural hazards, but some people also believe that there is an influence, there is an effect of climate change on these hazards, okay? So, given that we recognize that most of the so-called natural hazards are related to climate change, and given that these natural hazards bring a lot of threats to humanity, a lot of risk, if we look at the impacts of extreme events, of the impacts of socioeconomic events in general, we recognize that the natural hazards play a key role. They are responsible for the majority of the impact. So they generate a risk. So this is why, a real risk, this is why in climate change, there is the opinion that decision-making should be risk-based. And this is why then we deal with risk-based design, adaptation design, and not, for instance, cost benefit. We don't get into the details of cost benefit. Actually, it is also an important component, but what is more important is that we make an efficient assessment of the risk, whatever it means, induced by climate change through different events, different natural hazards, and then we select priorities basing on a risk assessment. I say whatever it means because we didn't define what risk means, okay? Just realize that I mentioned hazard and risk, they are two different things, okay? When I say natural hazard and I say the risk that is caused by natural hazards, they are two different stories, and we will see what the difference is, okay? It is quite understandable, quite obvious that the impact of a natural hazard depends on its frequency. So the risk, let me use impact and risk as synonyms so far. The risk originated by a natural hazard is related to its frequency. this is quite obvious. When you think of the risks in our everyday life, like the risk of making a car accident, we recognize that the risk of making a car accident is higher with respect to the risk that I run when I take a plane. Okay. And why is that? Because if we look at statistics, we see that the frequency of people that get injured by car accident is probably 2 orders of magnitude higher. The number of people that are hit that are injured in a car accident is probably 2 orders of magnitude than the number of people that are injured for a plane crash. And then the plane crash, of course, it's something that is more it gets more visibility because it involves a lot of people, and usually, unfortunately, it's a major problem because of a number of lives that are lost. But if you look at the statistics, you understand that the number of people and then the frequency of people that get a problem for a car accident is much larger. And therefore, we understand it's quite obvious that if the frequency is larger, we estimate that the risk is larger as well. Okay, the same if you look at other possibilities of getting injured, like other risks. I mean, we usually look at the frequency, and therefore, if we have to assess risk, to estimate risk, it's clear that in some way we will be called to relate the risk to the frequency of an extreme event, the frequency of something that is threatening us. And frequency means probability. And this is to justify the fact that we will have to dedicate some attention to refresh some probability concepts, because if we want to understand climate change, we have to understand probability. This is for sure, okay? For sure, because probability means frequency. And therefore, for the reasons that I just mentioned, frequency is an essential component. So what is the frequency of floods and how the frequency of floods is impacted by climate change? Frequency is, let's say, from a narrative point of view, is a synonym of probability, okay? Now, risk. What is risk? So look at this question. What is risk and how can we estimate it? There is quite large literature on the subject, and I want to estimate you. I want to give you an example. I am self-serving because, of course, I know better my papers than the papers written by others, but I may also give some other examples on how risk is estimated and how risk is related to climate change. Let me open another window, and let me search for Google impossible flood, and let's see if I get there soon. Yeah, the sword of Damocles of the impossible flood, and this is a paper that is under review, and you can understand, you can read, this is an easy reading. If you are interested in risk estimation, you can read here, and preprint, you see it's a preprint, it's under review. And you can also, if you are interested, there is also the review online with our response to the reviewers. And here you, as I said, it's an easy reading, and you can get an example of how risk is estimated. And this is using a kind of analogy, because why impossible flood? Because very often we are hit by floods that we believe are impossible. Okay, and as I said, it's an easy reading. It's not necessary that you read it, absolutely not necessary for your exam. Okay, so our risk, what is risk then, and how can we estimate it? Okay, when we deal with the natural hazards, the literature suggests that risk is estimated based on some premises. And the first premise is that the risk, let's call it R, induced by a considered event, is given by the combination of three factors. I call them factors because indeed the risk is expressed. Look at this equation here. Risk is expressed as the multiplication of these three factors, which we called PVE. P stands for hazard, okay? E is exposure and V is vulnerability. There are some contributions by the literature which add a fourth factor. Let's stick on this definition, which is very easy. You see, it's a simple multiplication. It's very easy to remember. And as you will see also, the concept is very easy. So first of all, let me anticipate. What is the unit of risk? The unit is the unit of the damage that you are estimating. So basically, at the basis of risk estimation, there is an estimation of the damage. As we will see, damage gets into one of these three factors. Okay. So the unit of risk is the unit of the damage. The damage is economic. Okay, so risk is then expressed in economic terms. The damage is loss of life, then risk is expressed in the unit of number of lives that are lost. Okay. It is very easy to understand then what is risk. So let's talk about money. Money because is less emotional with respect to loss of lives. Okay, let's talk about money. It's less emotional. It's something really that we can discuss freely. No, so the risk is measured in the money that I have to take from my pocket after an extreme event. Okay, it's very clear. Okay, so what are these three factors then? Hazard P, exposure E, vulnerability V. So what you read in the second point, R is a measure of the expected damage during an assigned time period given by a considered event. So what is the damage that I get in 1 year? By a considered event, by a flood. Okay, so this is the measure. Okay, so what is then, let's focus on the single factors. What is then P? P is hazard, as we said, is given by the probability of the considered event to happen in the location of interest in a specific context, it's written here, and the assigned time period. So every year, what is the probability of getting a flood? Probability means frequency. So every year, what is the frequency with which I get floods? If I get, on average, 1 floods every 10 years, the probability will be 1/10 every year to get a flood, okay? This is very simple. I mean, let's assimilate probability to frequency. Frequency is estimated as the number of events divided by the period. So if in 10 years I have 1 flood, the probability each year to get a flood is 1/10 because it's the frequency in each year of the flood. And it's clear that the risk must be related to the frequency of the event. If an event doesn't happen, I have no risk. If an event is impossible, like the impossible flood, which is not impossible, but let's assume that an event is impossible, the risk is 0. Why? Because the probability is 0. P is 0. The frequency is 0. If an event occurs very frequently, of course, the risk is higher in terms of economic damage, but also in terms of anything else. Okay, so P is the frequency. It's the hazard, it's the frequency, it's the probability. Because as we said, probability is a synonym for frequency so far. We will see the difference, okay? Vulnerability. Vulnerability is, let's drop the term probability here. Vulnerability is a measure between 0 and 1 that expresses that the system is damaged at a certain level if the considered event occurs. So let's suppose that you have a city. The city gets a flood. What is the measure of the damage of that occurs between 0 and 1? So let's suppose that you have a levee protecting the city. The levee cannot be overtopped, absolutely. So even if the flood occurs, vulnerability is 0, because I don't get any impact, because there is the levee. Or let's suppose that you don't have any protection. So if you get flooded, the whole city, if you get a flood, the whole city is flooded, then vulnerability is 1. So it means the event occurs. Let's assume that the event comes. What is the extent of the damage? Between 0 and 1. Okay. Once again, vulnerability 0 means no risk. No risk, absolutely. If the levee is so high that can't be overtopped, it's impossible. Risk is 0. Now, what is E? E is a measure of the damage if the event occurs and vulnerability is 1. So the event occurs, the city is not protected, is flooded. What is the economic damage? It's E. So E reflects the presence of goods exposed. This is why we consider exposure to the considered event. Now, let's suppose that the event occurs, vulnerability is 1, risk is equal to E, to the exposure. The city gets a flood, gets inundated because there is no protection. So what is the damage? And this is bringing the unit, okay? The unit in terms of money or loss of lives. I think this representation is nice because it is very simple. It's very simple. Also simple to remember. And I think it clarifies what are the components of risk. Frequency, probability, P. Once again, if an event is very rare, then risk probability goes down and risk goes down. Vulnerability, so meaning it's adaptation. Vulnerability, you understand, it's adaptation. So vulnerability means I accept the event, I accept climate change, and then I get protected against it. This is vulnerability. And then there is exposure, which is the damage that I want to avoid. Now, you understand that what is the impact of climate change on these 3 factors? It's on P, it's on probability. So if climate change is increasing probability, it's increasing the frequency of the flood or the drought or the windstorm or the heat waves. This is the way climate change affects risk. So climate change gets into this equation through P. Adaptation gets into this equation through V, but also through E, because we could also decide to reduce the exposure. So why building in an area that is exposed to flooding, building an industrial settlement which has a high value? We may reduce exposure, okay? So I think, as I said, this representation is nice because it's very clear. Now, we don't have to forget that it looks simple, but actually, when we go to the estimation of the single factors, it becomes a little bit more complicated because
You understand, estimating probability of an extreme event is already a difficult task in itself. If you put climate change into there, it becomes even more difficult, because actually we don't know how probability frequency of a natural hazard is influenced by climate change. Of course, we know that in principle, and it's quite obvious to assume that the frequency of floods is increased after climate change, but how much? How much is the key question if we want to make a design. And we don't know how much, actually, because we know that we have models, but the models are uncertain. So there is no clear guidance to engineers and also to policymakers on the quantification of climate change and its effect on probability. So as to estimate P is a difficult task in itself, because we have to know the probability theory, and we have to know how to apply it, probability theory, in absence of data. So it's already a difficult task in itself, even without climate change. And then we have to put climate change there, which is not easy. Now, vulnerability. Vulnerability is a socioeconomic exposure. Let me start with exposure, given that I mentioned that it's a socioeconomic problem. Estimation of exposure is a socioeconomic problem. It's not really a task for the engineer, or let's say it's the task for a team where the engineer may play a role, but we also need, a component of economics, an expert in socioeconomic development. And let's not to forget that exposure is not a constant. It's not a constant. It depends on the magnitude of the extreme event. So if a flood occurs, not all the city is flooded, depending on the intensity of the flood, on the magnitude, depending on the probability of the flood, we have to expect that exposure increases for increasing magnitude of the flood. Or in other words, if I decrease P, less frequent flood, less frequent means that higher magnitude, okay, higher magnitude. Decreasing probability, increasing exposure. Why a less frequent flood has a higher magnitude? But this is by definition. I mean, if I look at the frequency of big floods, it's very low. If I look at the frequency of ordinary floods, it's much higher. So the same for probability. The probability of a very big flood is low, but it has a high exposure. Is it clear? A big flood produces a bigger damage, and therefore the exposure of a big flood is higher, but lower probability. So this is an interesting reasoning, because you understand that we don't have to forget the events with very low probability. Because an event with very low probability, you may say, and very frequently, this is the suggestion for the policymaker. Forget about the flood that is really nearly to impossible. What is the purpose of the paper that I showed you before? The purpose is beware. You are forgetting the contribution to risk of floods with very low probability, because this looks convenient. And also because the technical guidelines don't tell you to get protected against a flood that occurs once on average every 1,000 years. They say get protected against a flood that occurs quite regularly. So you're forgetting the flood with very low probability, but don't forget that this flood may have a very high exposure. And therefore, if it comes, the flood with the very low probability, it's a disaster because the exposure is large. And the vulnerability also depends on the probability. Sometimes we get protected against ordinary floods, but we don't get protected against the flood that may occur once in 1,000 years on average. Very low frequency, very low probability. We don't get protected because it's not convenient, and the guidelines don't tell us to get protected. So if we get this impossible flood, the result is that we are vulnerable and we are highly exposed. So it's a disaster. And this is what occurred recently, like in Germany in 2021. This was a very rare flood, very rare. And why they got so big damage? Because they were not expecting it. They were vulnerable and highly exposed. Other examples, last year in Libya, the flood that occurred in Libya, and it was really huge. And the reason is that it was very nearly to impossible. And I mean, unfortunately, there are several examples. And an example that is not recent, the flood in Florence. The flood in Florence in 1966. It was huge, with a huge impact. But, and they were not expecting it. It's very, very rare. So the city is vulnerable and with high exposure. And today's is even worse because Florence is in the same conditions in terms of vulnerability. Vulnerability is at the same level as in 1966. The exposure is increased a lot for reasons that are clear, socioeconomic development. And the probability, probably, after climate change and after land use change is increased. So Florence is exposed probably to a higher risk with respect to 1966. But still, I mean, there is the feeling that it's very unlikely that we get another flood like in 1966, and so there is no action. So basically, we understood how a risk can be assessed, and we will discuss now how to estimate the single terms in the future. Any question? It's interesting, isn't it? Okay, I hope so. Okay, so please come forward with proposals for presentations. It can also be delivered online, even if I prefer that if you can make the effort to come here. But if students cannot attend in presence, a presentation can be also delivered online. Thank you very much. Also, thanks to the students that are remotely connected. Bye-bye.